All right, so the next one that we're going to do are when these Riemann sums don't begin at 0. And let's be real, up to this point, any of your examples that you've done have all started pretty much at 0 in the homework questions. So what does that look like when it doesn't start at 1? We've experienced some of that when we've done our number lines and we've said, okay, you have a missing number in the number line and it didn't start at 0. And we've learned to adjust for that. But what does that look like when we're doing our Riemann sums? And more intensely, honestly, the n subdivisions. So let's just kind of do a quick little recap on how to do the Riemann sum with 3 subdivisions, something kind of simple, and then we'll move to the n subdivisions. Obviously, as always, we want to figure out how long our interval is, and again, that's 3. So that would mean with 3 subdivisions, we do 3 divided by 3, correct? And that would give me 1. So I put 1 on the outside, and I'm going to do 3 different heights. The first one that I'm going to do is not at 1, but where's that first bar going to be? If I'm splitting this into, where is this number? It's obviously not at 1, it's at 3. Well, how did you get that number? If you thought about it, you basically said, hey, I'm going to do 2 plus that 1 that you're dealing with here. And that gave me f of 3. So that's how we did that. And then the next one would be f of 4, and the next one would be f of 5, quite simply, right? And then you'd plug it into the equation, so I'd have 9, and I'd have 16, of course, because that's 3 squared and 4 squared and 5 squared. And we would add these two together, and so we'd get 50, no problem. Well, let's look at how this looks with n subdivisions. We still would have the 3, and we would be dividing into the n subdivisions. And much like the examples we've been doing in the last few days in class, we would just at least set up enough so that we can get a pattern going. Some of you might even be able to skip this step in terms of setting up the pattern because you already see what's going to happen here. But maybe not. So let's just work on these and just break it right down. So the first bar, this first question mark, so to speak, where is that going to be? I want you to think about this as being, hey, we're starting at 2, and I'm going to add whatever this amount is. I'm going to add 3 over n to that, whatever that width is. If there was 3 subdivisions, then I'm adding 1, because that'd be 3 divided by 3. If there were 6 subdivisions, I'd be adding a half, or whatever that is. So the next one, okay, would mean, so if this is 2 plus 3 over n, and whatever that number is, then the next one would mean I'm going to add another, so this one would be adding another 3 over n, because that's what that distance is. And so just to write what that looks like, I'm going to drop it here, would be f of, it would still be 2, because that's our starting point, and it would be 2 times 3 over n. And the next one would be f of 2 plus 3 times, in other words, 3 of those widths. And we would keep doing that, still be 2 plus, but it would be n of them. This becomes a little bit more tricky, I'm not going to lie. So as we do this, what's going to happen, we're going to take this and we're going to plug it into the equation. And in our case, that would mean that what we have here, so we have the 3 over n, I would have 2 plus 3 over n, and I put that in place of x squared. That's what that would be. Plus, then I would have 2 plus 2 times 3 over n. We put that in the spot of x, and that would be squared. And then it would be 2 plus 3 times 3 over n squared, da 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 da. And we would keep doing this until we had n. Now, this is really like a lot of the algebra that we've done so far in all of your high school career. The truth is here, where most people make mistakes, is they right now want to pull out those extra pieces. But you can't do that because this squared somehow limits us to do that. We have to be, I guess, aware of the fact that this is not just 2 squared, this is not just 3 over n squared, but there's a middle term even involved. So what we're going to do is we're going to try to rewrite this without actually multiplying it out first, and so that you can actually see what's going on here. I don't know, maybe this will help. So let's see if we can do this. If you can look at this instead of saying, okay, we've got 3 over n on the outside, that's a given. And can I rewrite this so that it's something, in other words, I'm going to write this with the sigma notation. I know it's going to start at 1. I know it's going to go all the way to n. Bear with me here. So what this would be is 2 plus, right, 3. And the way that we write this is 3k. And you're like, k, where'd the k come from? Because the k is basically saying, hey, k is going to start at 1, and we're going to keep plugging those in 1, 2, 3, 4, and that's what's multiplying. That's this number here that's multiplying through to that 3 over n. And before I can pull anything else out, I want you to see what's going to happen here is we're going to multiply this puppy out. So we're actually going to do 2 plus 3k over n times 2 plus 3k over n. Now just watch this. This is really neat. So we'd get 4. We would get 12k over n plus 9k squared over n squared. If you need to, I want you to take a moment. I want you to pause the video, and I want you to multiply that out yourself so you can see where those terms come from. But that, when you multiply that out, whether you do it mentally or otherwise, you're going to get those terms in there. Now what I want you to do, okay, is we're going to write this so that we have the summation of 1, the summation of k, and the summation of k squared, because those we know. And really, what you're basically doing is saying, hey, I've got that 4 in front. I've got a 12 over n in front of that summation of k, and I've got a 9 over n squared in front. I tell you, these are intense, right? Keep going. What does this mean? Well, in place of the summation of 1, I'm going to put n. In place of the summation of k, I'm going to put 1/2 n squared plus 1/2 n. In place of the summation of k squared, I'm going to put 1/3 n cubed plus 1/2 n squared plus 1/6 n. And then I'm going to simplify this mathematically. So what I would do here is 3 times 4 is 12, and notice the n's would cancel out. Plus, I would have, right? Is everybody okay with that? And maybe maybe I should leave it like this. Maybe I should do this first. Apologize for that. Let's leave the 3 over n on the outside. Maybe that's just too much to handle at the same time. Let's just simplify these. 12 divided by 2 is 6, and that would leave you with an n. And then you'd have 6, and the n's would cancel. Then I'd have 3, and I'd be left with an n plus 9 over 2, and the n squareds would cancel. Then I'd have 9 over 6, and I want you to notice that there'd be an n left in the denominator. Now we're going to combine like terms. Again, I'll leave this 3 over n here just so I don't do too much at one time. I would have 4 plus 6 gives me 10. I'd have 13n, okay? Plus 9. Did I do that right? I'm sorry. That's silly. I almost grabbed the 6n here. So I've got the 4n, the 6n, and the 3n taken care of. Now these two can combine together, which gives me 21 over 2, and then I'd have the 9 over 6n. Multiply through, we would get 39, the n's would cancel. I'd have 63 over 2n plus 27 over 6n squared. Now here's the coolest thing. What did that just tell me? If you remember from the last couple of days, what we have been discovering is the fact that this number here is telling me that this is the exact area. That means that I know that the area underneath this parabola between 2 and 5, all right, between 2 and 5 is in fact 39. I know that. That's the part I know. And then this is our error terms. This tells me how much of that excess, if I had one subdivision, it would tell me how much excess I would actually have. And we've been doing that, at least I hope I've been doing that in class with you, that what you would have, let's just say it was one subdivision, okay? Then that means how you would use this is you'd have 39, you'd have 63 over 2 times 1, plus 27 over 6. And so just to simplify this again, right, that doesn't work out nicely, but 27 over 6, can we divide that? Both of those we can divide by 3, giving me 9 over 2. Now we could combine those two, giving me 72 over 2. Hey, that's 36. That means 39 plus 36. That would give me 75. That means that if I did one subdivision, right, I would have 36 in excess. And if I had done this with one subdivision, meaning one rectangle, I would have gotten an answer of 75. You don't believe me? Go ahead and give it a shot and see that, in fact, if I had just drawn one little box, boom, boom, that this here would have totaled that 36 and that excess. So I want you to see the beautiful part of this n subdivision. It allows us to see. And there's even more patterns to observe because Riemann didn't stop there. As cumbersome as this all is, and you might have thought, how did he even go about this? He just kept cranking out numbers and cranking out the math and seeing. And then, as he started to see, wait a minute, How is it that there's always this kind of a relationship when I want to find the exact area and an equation? I'm going to tell you, it's beautiful. And, well, as I told you before, you're going to be quite upset with me how simple it is in comparison to what we're doing here. So that just gives you a little smattering, another example that you can use and refer to. So we'll work on these tomorrow in class.